Hi everyone. The goal of this video is to learn what an exponential function is. By the end, you should be able to identify, graph, and evaluate these functions. I actually think exponential functions are probably one of the functions you understand more in your everyday life, maybe second to linear functions. So this one, while it is new information, it shouldn't be new to the idea. So I'm going to give you an example to begin so you can connect this to what you already know. Here's one example of an exponential function. Miss Mancini just joined Facebook over the weekend. She currently has 5 Facebook friends, but this number is going to triple each month. So how many friends will she have in 1 month, in 2 months, in a year? So I started with 5. At the end of the month, that's going to triple. So I'll have 15. And then at the end of the next month, 15 is going to triple. So I'll have 45. And at the end of that month, that's going to triple again. So I'll have 135. And at the end of that month, that's going to triple again. So I'll have 405. I know, I'm so popular, right? This is an example of an exponential function, or something you may have heard is exponential growth, because it's multiplying by an increasing number of 3's. So what that means is from here to here, I had to multiply by 3. And then I had to multiply by 3 again. So what this means is from here to here, I had to multiply by 2 factors of 3, so I multiplied it by 9. So an increasing number of 3's. So 1, 3, 2, 3. Now from here to here, I had to multiply by 3 again, and by 3 again here. But if I'm starting from the beginning, from here to here, I had to multiply by 1, 2, 3 factors of 3, so I had to multiply by 27. So an exponential function is when you're growing by an increasing rate, which we'll get back to that idea many, many times. Another example of exponential growth is something you've seen a lot this year, and that's compound interest. So I'll come back to the general idea. Let's fill in the formula first. So I invest an initial amount of $1,000. P is your initial. Okay, and I have an interest rate of 5%, so that's 0.05. If interest is compounded quarterly, okay, so that means I'd compound or receive the interest 4 times a year. There are 4 quarters in a year. I want to know how much money I'll have in 10 years. Okay, so T is my time, N is how many times I compound, R is my rate, and A is your final value. So if I plug that in, I'll have 1,000 times 1 plus 0.05 over, I'm compounding 4 times, raised to the NT, which is 4 times 10. Okay, so compound interest is an example of exponential growth, and let's talk about why that is. Now in this case, well, we'll get back to that in a second, but basically what this means is that every year you earn interest, you're earning more and more because it's starting to compound on what you had the previous year, not what you started with. So like if I have $1,000 in my account, it's going to grow a little bit, but the next year it'll grow a little bit more because there'll be more money to compound. And then like 10 years, it'll start growing a little bit more because I'll have more money to compound. Another reason why this is exponential growth is because you're raising all of this to an exponential power. So exponential growth has to have something to do with exponents. We'll come back to this example a lot, but I just want to start getting you in tune with what it looks like to be an exponential function or what it means. Now for the mathematical specifics, this is what an exponential function looks like. Okay, it's got some base, and your variable is in the exponent. Okay, now the base tells you by what factor your function is growing. So this one's growing by a factor of 2, this one's growing by 1/2. So think about what that means. If I make a table to go ahead and graph this, we can see a little bit further what this means. So if my x is 1, my y is 2. If my x is 2, my y is 4. If it's 3, it's 2 to the third is 8. If it's 4, then we have 16, so on and so forth. So if I plot those, I'll have 1, 2, 2, 4, 3, 5, 6, 7, 8, and 4 is going to be up here at 16, somewhere over there. Okay, I suppose I should also include 0 and some negative numbers just to get an idea of really what's going on here. So if it's 0, anything to 0 power is just 1. Negative 1 would be 1/2. Negative 2, again a negative exponent flips it essentially, would be 1/4. Okay, so going the other way, I have 0, 1 is my intercept. At negative 1, I'm at a half. At negative 2, I'm at a fourth. And the output can never be 0 here, because if you keep raising it to a power, then it's going to approach this axis, but it's never going to cross. So it's going to look something like this. And I just guesstimated on that point up there. Okay, so you're going to get increasingly smaller fractions, but you're never actually going to get 0. So again, if you think about my original example, an exponential function means increasingly growing by a certain factor. So this is growing by an increasing factor of 2's. So it starts growing kind of slow, and then it grows very rapidly at the end. Okay, let's look at 1/2 raised to the x. Do the same thing. Okay, so if my input is 1, my output is a half. If my input is 2, my output is, well, raise this to the second power. You're multiplying 1/2 2 times, it's a fourth. If I raise it to the 0, again, anything to 0 is 1. What happens if I raise this one to a negative exponent, though? So like negative 1. So then I'll have 1/2 raise the negative first, which essentially just flips it, so it'd be 2. And negative 2 would be 4, so on and so forth. Negative 3 then would flip it, and then it would be 8. Negative 4 would be 16. So this one looks something like this. Negative 4, we're going to shoot up here. Negative 3, 1, 2, 3, we have 8, 5, 6, 7, 8. Negative 2, we have 4. Negative 1, we have 2. So it almost kind of looks like the other one, but something slightly different happens here. So what's different about this graph versus the one we just looked at? And the answer is, it's going to reflect. Shouldn't go up there, I just can't draw. It's going to reflect over the y-axis there. And if you think about it, this makes sense. So this one's growing by an increasing factor of 2, so it's going to get bigger rapidly. Whereas this one starts bigger and it's going to shrink. It's going to get smaller as we go on. Because the growth factor here, start calling that a growth factor, is 1/2, which actually is going to make it shrink. So if you multiply by 1/2 an increasing amount of times, it's going to get smaller and smaller each time. Cool, right? Okay. Another example is the graph of f of x equals e to the x. The reason I'm giving you this example is to talk about what e is just a little bit. E is a mathematical constant. So although it's a variable, it's actually a number. Like pi has a value, it's 3.14, yada, yada, yada. E also has a value. So if you ever see an e, that number is equivalent, and I'm rounding this, but it's equivalent to 2.71828, on and on and on. I always mention pi when I'm introducing e because they have the similar property that it is irrational. Craziness. Okay, more rational numbers here. You may also heard this called as Euler's number. Now, I know it looks like Euler or something. It's pronounced Euler, or that's how most people pronounce it. I don't know, I put a dot dot there. This is called Euler's constant, or Euler's number. Again, we'll look into this more in the future. It's used a lot with logs. You'll have to know it to talk about natural logs, which we'll get into. It helps us with interest, compound interest. It's going to help us with exponential growth and decay and all the stuff we're getting into. So this is a very, very brief introduction to what E is. We will talk about this a lot more in the future. But it's just some number, so it's like having a base of 2.718, so on and so forth. And the last thing we're going to talk about in this video is how to transform an exponential function. And the good news is that transformations are transformations no matter what function you're looking at. So everything you know from transformations from chapter 1 applies now. So for example, if you have x minus 4, it's going to shift the x coordinate, and it's going to shift it positive 4. Okay, so whatever's attached to the x, lies to you, and it does the opposite of what you think it's going to do. So you think this is going to go left 4, it's going to go right. Okay, or a multiplying factor to the whole function is going to scale the y coordinate by 2. Okay, so if you scale the y coordinates by 2, it's going to get like taller essentially. So you can think about what that means. E to the negative x, you're making all of your x coordinates negative. So if your x coordinate was over here, it's now going to be over here. If it was over here, it's going to be over here. So this is going to reflect across the y-axis. Whereas if you make the whole function negative, you're really making your y coordinates negative. So if it was up here, it's now going to be down here. Or if it was down here, it's now going to be up here. So this is going to reflect I don't know why I put an X. I'm just going crazy today. It's going to reflect across the x-axis, so to go here to here. Okay, so I don't want to talk a ton about transformations. I just want to say if you're transforming an exponential function, no matter what it looks like, the transformations are the same as if you're looking at any other function. The only difference is what the structure of the parent function looks like. So that's all I want to say. You should now be able to graph exponential functions. You should be able to figure out how to transform them. You should understand the structure and what they look like, and you should know some applications of them. And we will practice this more later, so please come with questions.